Here is the combined summary of the 4 pages. This study leverages hydrodynamical simulations of merging galaxy clusters to probe the potential of these natural dark matter colliders for measuring the interaction cross-section between dark matter particles. The Bahamas suite of cosmological simulations is employed, incorporating both self-interacting dark matter, SIDM, and ordinary matter in a universe with a massive mediator particle. Simulations are run with varying DM interaction strengths, spanning the range of empirically allowed cross-sections. The analysis focuses on the 300 most massive clusters in each simulation volume at redshift z equals 0, selecting those with one or more subhalos of at least 5% the total mass within 4 mpc. This yields approximately 100 clusters and 135 subhalos in each simulation. The study finds relatively small separations between the different components of matter, with a mean component separation of 33 plus or minus 2 kpc and an RMS scatter of 49 kpc. The research highlights that future studies adopting a similar selection strategy should easily be able to maintain or increase these values, as new clusters with large separations between galaxies and gas continue to be found in X-ray or Synyavzildovich surveys. The study quantifies the offset between a cluster's different components using their position, as opposed to using quadrupole moments. The analysis of galaxy clusters and their subhalos in the context of SIDM simulations is performed using the Bahamas suite. The spatial offsets between stars, gas, and DM in these systems are measured using a shrinking spheres method to determine the 3D location of each component of matter. Median and 1 sigma-like uncertainties are employed for measurements, and the results of the measurements of beta parallel and beta perpendicular from simulated merging clusters follow approximately Gaussian distributions. The importance of averaging measurements from different systems is discussed, with the use of an inverse variance weight to obtain a more accurate understanding of the dynamics of SIDM. Researchers investigated the offsets between galaxies and dark matter in simulated colliding galaxy clusters, comparing the self-interacting dark matter (SIDM) model with the standard cold dark matter (CDM) model using the Bahamas suite of hydrodynamical simulations. The analysis focused on measuring the fractional offset between galaxies and DM, denoted as beta parallel, in both main halos and subhalos. The results showed that the scatter of DM offsets increases with SIDM cross-section, and the median DM offset also increases with the cross-section, consistent with the model proposed by Harvey et al., 2014. The study explored potential selection effects, such as the average measurement from many colliding systems, and the variation in offsets with time since collision, although these aspects were not fully explored due to dataset limitations. The best-fitting parameters of the model to the measurements were calculated using the Python function scipy. Optimize, minimize, and the results are presented in Table 2. The median DM offsets were also measured for 2D and 3D projections, showing similar trends. The authors highlight the importance of considering systematics in the measurements, particularly the bias when measuring the position of one halo in the outskirts of another. They confirm this bias by comparing positions measured using all particles with those measured using only bound particles. The interpretation of the average measurement from many colliding systems assumes that the offset is universal, but this may not be the case if the offsets vary with time since collision. The authors investigate the possibility of testing SIDM models using galaxy cluster mergers, utilizing cosmological simulations to measure the offset between dark matter and galaxies, termed bulleticity, beta parallel. They find that beta parallel increases with the interaction cross-section, matching predictions from an analytic model, and can be used as a promising test of SIDM. The authors forecast the ability of future surveys to rule out the null hypothesis of non-interacting dark matter using beta parallel measurements, estimating that a large sample of merging clusters would be required to achieve constraints relevant to particle physics. The research paper investigates the merging of galaxy clusters and self-interacting dark matter, SIDM, through simulations, focusing on the weighted median fractional offset between galaxies and dark matter as a function of the SIDM cross-section. Figure A1 displays the results, with the top panel showing the weighted median fractional offset and the bottom panel displaying the perpendicular control test. The red circles and blue triangles represent calculations using 3D or 2D projected information, and the curves show the best fits of the Harvey et al. 2014 analytic model to the measurements. Table A1 presents the best fitting parameters of the Harvey et al. 2014 analytic model to the measurements of the weighted median. Figures B1 and B2 display the distance between stellar matter and dark matter in simulations of colliding galaxy clusters, parallel and perpendicular to the direction of motion, respectively. The authors find that the weighted median becomes highly unstable when using inverse variance weights but is stable when using weights proportional to the square root of the variance, a scheme that is mathematically unjustified but may be worth considering in future analyses. The paper explores the occurrence of merging galaxy clusters in cold dark matter, CDM, and SIDM simulations, highlighting significant differences between these two models, particularly in terms of their impact on the spatial distribution of galaxies within galaxy clusters. The analysis is based on the distance ratios of galaxies to dark matter and gas, which are crucial for understanding the dynamics and interactions within these cosmic structures. The results show that as the cross-section increases, the distance between galaxies and DM increases, while the distance between galaxies and gas decreases, indicating a more scattered distribution of galaxies in SIDM models compared to CDM.